Hello, my name is Elliot Cassidy, and today I'd like to walk through the solutions from question 3, Juggling from the 2010 British Informatics Olympiad. If you haven't already, please pause now to review the problem statement shown on screen. This problem requires us to find the minimum number of steps to end with exactly n ounces in any jug, starting from all jugs being empty. Each step consists of one of three operations. 1. Completely filling a jug. 2. Completely emptying a jug. Or 3. Pouring one jug into another until either the source is empty or the destination is full. From any given state, the number of possible next moves is the sum of all individual fill and empty operations, which is 2 per jug, plus all possible ordered pairs of jugs for pouring. This structure naturally induces a tree representation. From a root node, where all jugs are empty, each node branches to 12 children, representing possible subsequent operations. This branching continues recursively, with the tree depth corresponding precisely to the number of operations performed. This means that the shallowest occurrence of a jug filled with n ounces of water yields the minimum number of operations required. When generating child nodes, we track visited states to avoid redundant checks. Revisiting a state would lead us down an already explored path, and since we are looking for the shortest solution, we can safely avoid these duplicates. If you're unfamiliar with graph theory, I recommend you read the section on graph theory in the Competitive Programmer's Handbook, which I have linked to in the description below. To calculate the minimum number of operations required to achieve n ounces, the intuitive approach would be depth first search. This recursive algorithm traverses each branch of a tree to its deepest level before backtracking. Since each node can branch to 12 children, this yields a time complexity of O of 12 to the n, where n is the tree depth, placing it in exponential time. Consequently, the number of operations required to traverse this tree increases massively as a tree gains layers. This makes depth first search particularly inefficient, considering we only need the shallow solution. Thankfully, there exists a graph traversal algorithm which is vastly superior to depth first search when finding the shallowest solution, breadth first search. This is how it works. All nodes at depth 0 are explored, then all nodes on depth 1 are explored, then depth 2, and so on, until a leaf node is found. When this method is used, the first occurrence of a jug filled with n ounces of water will also be the shallowest occurrence, which means we don't have to iterate through every path, making it far more efficient than depth first search for our purposes. In fact, the worst case time complexity of this code is O of A times B times C, where A, B, and C represent the capacities of each jug, which is much more efficient than the O of 12 to the n of depth first search. Now that you grasp the core concepts behind solving this problem, I encourage you to attempt implementing a solution to this problem yourself. It's an excellent way to solidify your understanding. Afterwards, you may find it helpful to compare your solution against my annotated solutions available in the GitHub repository linked in the description below. Furthermore, you may want to attempt question 3, shirts, from the 2008 British Informatics Olympiad, which is a similar question you can attempt to practice breadth first search algorithms. If you found my video valuable, I would appreciate it if you could leave a like. And if you'd be interested in more content like this in the future, please do consider subscribing. Thank you for watching.